Hi, in this video I'm going to wrap up the lesson on templates. These wrap-up videos again are not summaries of the lesson, but instead they're often a bit of a mix. We have summaries of important concepts that we covered throughout the lesson, and then we'll also have a few examples, maybe a few short bonus examples that I did not think warranted their own videos. A quick summary on class template and function template type argument deduction. The compiler cannot deduce the type arguments for a class template as I mentioned in this lesson. We have a quick example of an invocation of a print template function in the main function. In the first statement we do print the angle brackets and we explicitly specify int for the type argument. And then we also pass in an actual argument for the formal parameter between parentheses. So this will print out 55 to the console as we've seen in previous examples. And in the next statement we simply do print 55 between parentheses, and the compiler is going to use an int template argument from the actual argument because the actual argument is an integer in this case. For the next example we do an instantiation of an entity class or struct in the main function. We do entity followed by the angle brackets, and we have to specify explicitly the type argument, in this case int, then the name of the actual object or instance, in this case entity1. And if you want to pass in arguments for the constructor, then you have the parentheses and you have your argument list in there. But the point of this is the compiler cannot deduce the type arguments for the class template. If you have a class or struct template with default arguments for its type parameters, then we can use the empty angle brackets when we instantiate that entity, in which case the default type arguments will be used. In this example I have the smallest template function again, and it has one type parameter and two formal parameters. Both of those will be using the type parameter. In this case the type parameter is t, and of course it's going to return the smallest of the two arguments that we pass in. So in main, here I do smallest, I specify a type argument of int, and for the actual parameters between parentheses I provide 5 and 3, so it should print out 3 right here. In the second statement where I do cout again, smallest, I do not specify a type argument, but I do provide two integer actual arguments, so the integer is going to be deduced for the type argument. Then in this next statement I have float, so I have two floats here, and I provide that as a type argument, and I provide two float literals as actual arguments. And then you can do a char as well. I have capital A and capital Z for the actual arguments. In the next console output statement I do smallest again. I specify int as the type argument, and then I provide 5 and 3.45 for the actual arguments. This statement right here is going to print out 3 to the console. And you can think for a second why that is. Remember that we provide int here for the type argument, so that type up here is going to be integer. Okay, t is going to be int. That means both parameters are going to be of type int. And the second actual argument that we pass in is a floating point double. It's not a float, it's a double. And the parameter that accepts that argument is only going to keep 3. It's going to throw away the 0.45. Build around that. This is the output that we get for the first statement. It prints out 3. For the second one we get 2, as we would expect. In the third statement where we specify float for the type argument, it's going to print out 33.04, and then a for the next statement, and as I mentioned, it's going to print out 3 for this final smallest call where we specify int for the type argument. Now if we go and look at the output, we will get this warning: argument conversion from double to t, possible loss of data. That is because we are converting this literal right here, this double, to an integer. Again, that is basic stuff. I just want you to watch out for this sort of stuff when you use templates. And then here I'm going to comment this line out. You can think for a second why we get this error. This is ambiguous, right? If you think about it for a second, we are not specifying a type argument in this function call, so the compiler cannot deduce the type argument. Alright, with this call right here, the compiler can deduce an integer. That's because both actual arguments are integers, whereas here we have a integer literal and a double literal. This should work fine now. Alright, so that was just a bonus demonstration for you. A quick recap on type parameters. I'll talk about non-type parameters again in the next subsection. An argument for a type parameter can be any built-in or user-defined type. In other words, you can use integrals, floating point types, some custom types such as an entity or a vector, and of course you can have pointers or references to something. And you can also use const, so you can have a pointer to an entity constant, for example. I would like to reiterate that with user-defined types as arguments, you have to ensure that the appropriate operators are overloaded, and also remember that while I use type name for the type parameters, you can also use class. A few examples for you. I'll start off with a simple example using the print template function, which has a type parameter t and a formal parameter which is of type t. In the body I'm going to print out that parameter, but I'm also going to try and change it, so I'll just add 5 to that formal parameter and then I'll print it out here. And in main, I declare a variable x which I initialize to 55, and then I have this function invocation here. So note the type that I use is a reference to an integer. If you hover over the parentheses here, IntelliSense should show you the prototype for that. So the return type is void, the function is print. The type parameter is set to be a reference to an integer, so the formal p parameter is going to be set to what? A reference to an integer. Then I just do another console output after print. What is x? Well, we print out x again, and let's just build and run this. We basically pass by reference, so in the function call where we add 5 to the parameter, we're also modifying and adding 5 to the x variable in the main function. Whereas if you pass by value, I'll change the type argument here to integer, and now we pass by value, right? So in the print function it will print out 60, and after the print, in other words, x in the main function will remain unchanged and will remain 55. Of course, if you change the type to something like this, a reference to an integer constant, then this line right here is going to give us an error, okay? Because again, if I hover over this here, you will see formal parameter is now a reference to an integer constant, but we're trying to modify that formal parameter in the print function. Control B to try and build that, and you'll get a failed. You cannot assign to a variable that is const. Of course, typically in a print function you don't want to modify what you pass in. That was a simple example using a function template and using references to integers as the type arguments. In the upcoming examples we'll look at a couple of examples with pointers and with objects. I have this myContainer class template. It has a type parameter and a non-type parameter. The non-type parameter is going to be used to initialize the size of an array, which I just called marray for member array, and that's going to be of type t. I've overloaded the subscript operator as well, which is going to return a type of t as well, and it is going to return the member array at the index that we specify, that is through the subscript. Let's just go back to main here. I declare a size integer constant which I initialize to 3, and then I construct container1 and I use that myContainer template. And notice here the type argument, okay, this first argument here is an argument for the type parameter, but it's not just an integer or a char or an entity. As we used in most of the previous examples, this is a pointer to an integer, and I specify size, so that is going to initialize the size of the member array. In the next statement, I define and initialize 3 variables, 3 integers, x, y, and z. X initialized to 3, y initialized to 4, and then z initialized to 5. Next, I'm going to use the overloaded subscript operator, and for the first element, I'm going to pass in the address of x. Notice that I cannot just pass in x like this. If I hover over here, we get a red squiggly. A value of type int cannot be assigned to an entity of type pointer to an int. That is because this array right here is an array to type of what? So in other words, what will the type of the elements in the array be? Well, type of t, and we specify that here as pointer to int. In other words, because we have for container1 we specialize pointer to an int, the array member for container1 will be an array of pointers to integers. So all of the members in that array will be pointers to integers, alright? And so for that reason, how do we get an address? We do the address of operator. That is how we are going to do these assignments. So for element 2, I get the address of y, and then I also assign the address of z to element 3. Then I do this for statement. I set int I to 0, and as long as I is less than size, which is the constant right here. Right, this is why I mentioned in model 1.1 it's handy to have a constant like that you can pass in right here for your for loop. And I do console output and I dereference this. So use the overloaded subscript operator again, but I dereference whatever I get from that, because if I scroll up, this is going to return a reference to type of t. With the syntax right here, we are going to fetch an element, based on the subscript that we pass in. So if you pass in subscript 0, we are going to get back what? Well, the first element for container 1 is going to be a pointer to a type of int. Okay, and we basically return a reference to that. And we can do dereferencing right here. And if I build and run, this works fine. We get 3, 4, and 5 printed out. And another tip I'd like to mention is that pay attention to the IntelliSense helpers. If you hover over here, that is over the subscript operator, it will actually tell you what we get back. It shows you the qualified subscript operator to the right, and to the left we have myContainer, that is the template type. It has a pointer to an int for the type parameter and 3 for the non-type parameter, but pay attention to what it returns. It returns a reference to an integer pointer. Okay, and that will help you if you get confused on why your outputs give you results that you do not expect, such as, if I remove that, of course this will build a run if I do not dereference, but we'll get a bunch of addresses. So again, use the helpers that are available to you, IntelliSense and so on, and pay attention to your types. Okay, so I hope you found this demonstration interesting. This was just to demonstrate to you that you can use different types for your type parameters, such as pointers to integers and so on. Okay, this example builds on the previous example. We are going to use polymorphism and look at how we can apply that and how that may be useful with templates. So I have a base class with a virtual destructor and a virtual toString function. It simply prints out base toString. This is from the lesson on polymorphism. I have a class derived, which publicly derives from the base class, and that also has a virtual destructor. And this is going to override the toString function and print out derived toString. Base and derived are non-template classes. Whereas here I have the myContainer again from the previous example. This is a template class. The definition of myContainer is the same as in the previous example. I overload the subscript operator and I have this array member. Okay, main is going to be different from the previous example. I have this constant size again, which I initialize to 3. But then check out the definition for container 1. Container 1 is now going to be of this type, so the type argument is a pointer to a base. That means the elements in the array are going to be pointers to type of base. And the array is going to be size. Okay, so we pass in that constant. Then I just do a few instantiations here. I construct base 1, which is of type base, derived 1, which is of type derived, and derived 2, which is of type derived as well. Then I use the overloaded subscript operator to assign the address of derived 1 to element 1 using subscript 0. The address of base 1 I'm going to set for element 2, and then the address of derived 2 I'm going to assign to the third element in container 1 using the subscript 2. Okay, and then in the for loop I'm going to loop through the elements in that container, so container 1, and because those are going to return what? Well, if I do Ctrl-Shift spacebar with the typing caret between those square brackets within the subscript operator, then we can see the declaration or prototype for that function, or in other words the operator. Okay, we get operator, the subscript operator, int index, and what is it going to return? A reference to a pointer to a base. So we get a pointer to a base back from this, and from that we do toString using the arrow operator. Again, instead of dereferencing and then doing dot and then toString, we use the arrow operator. Okay, so let's see what we get. Build and run, we get derived toString, base toString, and derived toString. Remember, we do derive first, then base, and derive 2. Now this is just a simple example. myContainer and the array is going to be on the stack and not on the heap, so we don't have any objects on the heap. If myContainer has to manage objects on the heap, then of course this definition will get a bit more complicated. I just wanted to keep it simple for this example. But this is important when you use vectors and some of the other containers that are provided in the standard library. This type of understanding of templates and polymorphism will be really fundamental. Again, right here where we do derived, remember that we assign an address of a derived object to this here, and the container, so the array within the container, stores pointers to type of base. And thanks to polymorphism, those pointers can point to a type of base or objects that are a type of derived. And it doesn't matter because, remember, we basically turn on polymorphism using the virtual keyword. And so with this we can have an array of pointers to the base class, and those can point to objects of the base class or to objects of the derived class. And again, thanks to polymorphism, we will get the correct or the appropriate function invocations. Okay, I hope you found this bonus subsection interesting. A recap on template non-type parameters. A template non-type or value parameter can be an integral type, so an integer for example, or a char or a short, or even an enumeration. You can think of these as value non-type parameters, whereas we can also have a pointer or reference to a type, including another type parameter, and with that we reuse existing type parameters. Now I would like to note that floating point and non-type parameters require the latest C++ language standard in the project settings. Okay, and then you can use floating point parameters as a non-type parameter. I'll show that here in Visual Studio in just a second. An argument for a template non-type parameter can be any one of these things: a constant or literal integral. Basically this has to be known at compile time because it is often used to initialize the size of a container, such as the array in our array entity example. It can also be the address of a static or global variable, or an instance of a class or a struct. Okay, so recap on this: I have an entity struct template again, I have a type parameter t, and I'm reusing that type parameter t for a non-type parameter, which I'll just call tp. I have a getVal member function which is going to return tp. Okay, and the function returns a type of t. Then in main I can do a constant integer x, which I initialize to 55, and I can pass in here where construct entity. Okay, this is going to be of type entity with a type argument of integer, and I pass in x for the non-type parameter. Build and run, we've seen this before, that works fine. Now I can also pass in a literal, so either a constant as here or a literal. So I'll just pass in 5 for example, and that will work fine as well. But if I change this here to a float and I try and build this, we will get an error. And also I can change this here. This is basically what happened before. We specified float as a type argument and we had t here, so that was float, but float is non-standard. Can just comment that out, I'm not using that anymore. Now I would like to note that if we try and build this, we'll get an error, and we can go and look at that. The point of the demonstration is that I want you to pay attention to the error messages that you get. A non-type template parameter of type float requires at least std C++ latest. So we can go to project. Okay, we go to the properties for our project and C++ language standard. We can set this to std C++ latest. Now these are basically features from the latest C++ working draft. We have the C++ 17 standard, and then we have this one right here. So I'll apply that and okay. IntelliSense may not catch up to this, but if I build a run, you will see that this actually works fine. Alright. Another bonus section for you on type deduction for non-type template parameters. And just to show you another example of where we can use the auto keyword, the compiler can deduce the type of a non-type template parameter if it is declared auto. I would like to note that this is a C++ 17 feature, so you need to make sure to set that in your project settings. You can see an example of the syntax for the template prefix. For the first parameter I have a regular type parameter, and then for the second parameter I have a non-type parameter, and it has auto for the type. So based on the argument that we pass in for the non-type parameter, the compiler will deduce the type for that parameter. I have a quick example using the entity struct again. You can see I have a regular type parameter in the template prefix, and then I have a non-type parameter, and use the auto keyword. Based on the argument that we pass in, the compiler will deduce the type of that parameter. In the struct I have a toString member function, and I'm going to print out the member, which is of type t. Okay, just some member for demonstration purposes, and then it's going to print out the non-type parameter is, and then we print out that parameter. I'll call that ntp for non-type parameter, so I'll just change that. And okay, in main, I construct entity1, but notice how I construct it. I specify the type as auto, so it's going to construct an entity. I pass an integer for the type argument, and then 55 for the non-type argument. So the type parameter will be set to int, and then the non-type parameter will be set to 55. And then the compiler will deduce that that is an integer. I can hover over entity and IntelliSense will show me the type. It shows me entity1 is of that type, the entity template, with an integer and then 55. So right here I just set member to 55, and then I do toString. And I build a run. And that works fine. Member is 55, and the non-type parameter is also 55. I'll just change that here to 44. We can see that difference. Now the member is 55 and the non-type parameter is 44. I can also change that, and I change that to an H. Now of course this will be a char. The compiler will deduce that that non-type parameter is of type char, and we get 55 for the member, and for the non-type parameter we get H. If you try and do a floating point type, again you'll get that error of a floating point template parameter is non-standard. So if I build, again you'll get this error that I talked about. Go to project, properties. I mentioned that using auto for your non-type parameters requires at least C++17, and if we switch to the C++ latest and I click apply, then floats will work fine too. You can build a run, and that will work fine. It will print out the float. Change that back and go back to something like C++14 and apply. And if you try and build a run now, you'll get an error. A parameter cannot have a type that contains auto. So that is why, again, you want to switch to at least C++17. Apply that and build a run, and this will work fine. Alright. So just another quick tip for you, and another example of where we can use the auto keyword. Next, a summary or a recap on function overloading versus function templates. With function overloading, we can have the same identifier, so the same function name in other words, but you need to change the signature so you have different parameters, or maybe you overload on const, and there's also a potential for a different definition. Let's say you add a formal parameter or you change one of the formal parameters to a type of a class or a struct. Then again, it's often the case that you go in and change the definition. Now ultimately what you get out of the function may be the same. It may return some value such as an integer, but the point is that not every single function overload is going to be the same. But with function templates you have the same identifier, the same parameters, and the same definition, but it's going to use placeholder types. And remember, as we discussed in this lesson, if you want to use a class or a struct as a type argument, then you'll need to make sure to overload the appropriate operators. That is going to wrap up this lesson. As we've seen, templates allow for more generalized or abstract code, but the code can get complex. Error messages generated by templates can also be difficult to understand and to debug. We've looked at the issues that you can have with non-type parameters where you have to provide static or global variables, and those types of issues, but templates are really handy and you are sure to come across them in production code. Templates are used for many things in C++, including containers from the standard template library. Now with containers such as an array, you want to create a container of what? A container of integers, a container of characters, floats, or maybe some user-defined types such as our entity or vector examples. And so we specify that as a type argument. I want to create a container of integers, I want to create a container of floats or entities. From the standard template library we have containers such as standard array, standard vectors, and you'll see this template syntax with smart pointers, which are basically objects that manage the raw pointers that we've discussed so far in the course. You have a similar syntax for a different type of casting that we haven't talked about yet. And this lesson was really the first steps for the foundation needed for us to learn about these other topics such as vectors and so on.